the stock naming system. The lesson itself is fairly short. The examples here, though, are incredibly lengthy. Pause often, take a break, do something. I did not intend for you to watch this straight through. I just couldn't find a good way to clip it in editing and post that really made sense. So what I have here is basic stock naming system, naming of polyatomic ions, stock names with polyatomic ions, and then some of the other exceptions that come up. Again, take breaks. I did not intend for the video to be this long for you to watch this straight through. Also, be sure you have your periodic tables out as we go through this. Polyatomic ions. So first off, just a reminder, ions are charged atoms, and atoms get charged when they gain or lose electrons. Polyatomic means that we have many atoms bonded together behaving like a single ion. So when it comes to naming polyatomic ions, I have to give credit to Ed Esquerdo. He's giving credit on my periodic table in the bottom left corner. He's the chemistry teacher that taught me this first. He teaches down in the Cincinnati area, and I just went to a half-hour workshop that he taught, and he pointed out this pattern that he had figured out in college, and no one else had ever seen it or pointed it out. I'm not sure many other people even realize it's out there, but it's absolutely amazing and super useful for figuring out the polyatomic ions rather than just memorizing a big long list of them. Certainly, if you'd like to, I have plenty of lists of polyatomic ions that you can work on memorizing, but I think knowing this pattern is better. For those of you in general chemistry, as long as you pass the elements quiz and the polyatomic ions quiz, you'll be allowed to use my periodic table, so you'll have the pattern there as a refresher. For those of you in AP, you get the AP periodic table on the AP test, so you do need to work on memorizing these eventually, and I'll help you with that in class. But anyway, underneath the P block, there is the 33443, and that first row of numbers tells us the number of oxygen atoms in the 8 version of the ions. And then underneath of that, there's another row, 32321, and that tells you the negative charge of all versions. Really, it's almost all versions of those ions. So then we can figure out the formula of a polyatomic ion. Before I do some examples, there are a couple exceptions. Nitrate is the biggest exception. Nitrate, if you follow the 33443, 32321 rule, should be NO4 with a 3 minus charge, and it is not. Nitrate is an NO3 with a 1 minus charge. It's just a huge exception to this list of rules. Other than that exception, and it's highlighted in green to remind you that it's an exception, you can figure out not only all the 8 polyatomic ions, but also all the variations on the 8. And those would include per-8s, 8s, ites, hypo-ites, as well as bi and tri and theo prefixes on those. And for that, you'll go to the green box that's underneath the list of exceptions on the periodic table, and you adjust the number of oxygens. Generally speaking, the charge stays the same, and so then you can figure out all of the polyatomic ions, even ones that theoretically are out there but don't actually exist. Not that you'll be doing that, but there's more than enough polyatomic ions here on this chart. The list of exceptions is a little bit lengthy, and most of those exceptions you'll notice have metals in them, although there are a couple that are positively charged as well. Or there's the ones that are not oxyanions. Oxyanions refers to polyatomic ions that have oxygen in them. There are some that do not have oxygen in them, and this list of rules cannot cover those exceptions. But other than those exceptions, and they don't come up as often as the others, you can figure out all the polyatomic ions, and we'll do quite a few examples here. So the stock naming system is used for ionically bonded substances. Usually that's a metal bonded to a non-metal, but specifically it's cations or positively charged ions bonded to anions or negatively charged ions. And the reason for stating it with cations and anions is because of the polyatomic ions. Polyatomic ions frequently are anions. There is ammonium as the sole major cation, but those make it so that we should really state it as cations bonded to anions rather than metals bonded to nonmetals. Furthermore, the stock naming system also uses Roman numerals if there is a transition metal atom in there. Technically speaking, I should say transition or other metal. Technically speaking, there are 4 exceptions there. If you, oh my goodness, we're just going to restate this whole thing. Furthermore, the stock naming system, if there's a transition metal or an other metal, uses a Roman numeral, and I have shaded all the elements that need a Roman numeral on my periodic table in gray. There are, technically speaking, 4 exceptions to those: silver, zinc, cadmium, and aluminum. They do not form more than one ion, and because they do not form more than one ion, they always form ions with the same charge. It is not required that they have a Roman numeral. If you put a Roman numeral with them, I'm not going to penalize you. But they don't require it because they have only one charge. And that goes back to their electron configurations and the fact that they can gain or lose a different number of electrons to give them different charges or oxidation numbers. So when it comes to the stock naming system, you start out with the metals name followed by the non-metals name, and the non-metals ending has been gets replaced by IDE. Sodium chloride is the best example of this. Sodium, metal name; chloride, non-metal name, with the ending dropped and replaced with IDE. The IDE suffix tells us that it's an ion instead of an atom. So chlorine is chlorine atoms, chloride is chloride ions. Unfortunately, with metals, it's either sodium atoms or sodium ions. We don't change the metal's name, so I don't know which I like better, but I don't like having a blending of those two. Anyway, if the anion is a polyatomic ion, then the ending has already been replaced, the suffix has already been replaced, and you just use the polyatomic ion's name. If there's a transition metal, as I mentioned up above, then you need a Roman numeral, and the Roman numeral tells you the charge of the metal. So this is not the number of that metal that is in the compound, it is the charge of the metal in the compound. And I'll show you here in just a moment how to figure out the charge of these things through some examples. Although there's quite a bit of details here to go through, that's really all there is to naming these things, unless it's a hydrate. For hydrates, hydrates are crystals that have water trapped inside them. So the water isn't bonded to the crystal the same way the elements that make up the crystal are bonded to one another, but this one here is copper 2 sulfate, and it is a hydrated molecule. And that means that there are waters trapped inside there. And so in the formula, that will be written with just a dot, and then the number of waters, and the formula for water, H2O. And as a name, it uses the Greek prefixes again, just like the prefix naming system. And so this is a something hydrate. And I'm not going to tell you which it is right now because this is a lab that we do in class, and so I don't want to give away the answer at this point. But that simply means that there are waters in there, but it affects its mass, and it affects how we name it, and so it's important to mention here. But I want to emphasize this dot here is not multiply by. It is just how we note that there are waters trapped inside of this thing. It simply means that there are waters, and as far as figuring out the mass of this thing, or the molar mass of this thing, we just add everything just like always. And so that's a shortcut that works for figuring out charges. So if we do that here on the next one, calcium chloride Ca, calcium has a 2+ charge, it's right underneath magnesium. Chloride Cl, it has a 1- charge, and if we take those and we crisscross them, then you end up with CaCl2. And the crisscross thing always works as long as you make sure that it can't reduce. So the last example I have here, strontium Sr, it has a 2+ charge. It's underneath calcium. There. And then sulfide is sulfur, it's an S, it's here on the periodic table, and it has a 2- charge. You can see already that if we crisscross these two, or that if we take these two, we are only going to need one of each. But if we do the crisscross thing, crisscross these two, we end up with Sr2, S2, and that one can simplify or reduce down to SRS. As long as you make sure it can't simplify or reduce, you'll always get it correct with the crisscross rule. Always works. We can also do the reverse process where we name formulas that we already have written. So this is fairly simple. Na is sodium, and Cl is chlorine, and we drop the ending and replace it with IDE. Now, I know that looks like on chlorine, like I just replaced the end with the D, but that's not true for all substances. So I prefer to show you that it is dropping the ending and replacing it with a new ending. Lithium fluoride. Shoot, just said the answer there. LiF is lithium fluoride. The next one, Al2O3, that is aluminum. And oxygen ending gets dropped and becomes oxide. Notice the subscripts do not enter into the name. It's not necessary for them to be there in the name. As a side note, it is a little difficult to tell what the name of some of these dropped endings sound like, so I do want to read through them here real quick, and I'll highlight on the periodic table as I go. So boron becomes boride, carbon becomes carbide, nitrogen becomes nitride, oxygen becomes oxide. The halogens are the simple ones because they all end in INE, so fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide, astatine becomes astenide. Septium hasn't been discovered yet, so right now we don't have to worry about that, and even once it is discovered, there's probably not going to be in large quantities enough to make compounds, so we don't really have to worry about it. Silicon becomes silicide, phosphorus becomes phosphide. I think phosphorus and oxygen are tied for the most number of letters dropped on an ending. Sulfur becomes sulfide, arsenic becomes arsenide, selenium becomes selenide, tellurium becomes telluride. All the other things on that side of the periodic table are metals or noble gases, and they don't form compounds this way. They're not the negatively charged thing at the end, so we don't have to worry about that. I'm not going to penalize you if you drop too much or too little at the ending. I am going to penalize you if you don't drop at least some of the ending and replace it with IDE. So just so you know how I intend to grade it, and you'll get used to how most of these are named. The halogens, like I said, are super easy, and the ones that we see most commonly by far are nitrogen, oxygen, sulfur, nitrides, oxide, and sulfide. Excuse me. Polyatomic ions. So polyatomic ions are groups of atoms working together as an individual ion, and they form a thing that behaves like it's just one ion. There is a pattern to the formulas and a pattern to the naming. In the past, I've just said memorize it. When I was a student, I was just told to memorize certain polyatomic ions, and I would cram for a test and I'd forget them eventually. I did eventually learn them after a few years of taking chem, but a few years ago, quite a few years ago now, I had another chemistry teacher, Ed Esquerdo, who is given credit here on my periodic table down here, showed me a pattern. He's a teacher down in the Cincinnati area, and he showed me and some other teachers a pattern that is absolutely amazing, and I based my periodic table off of his, and this pattern is super useful. So first off, we're going to look at how to name ions, and then we'll look at those ions in compounds inside of substances. So, sulfate, first off, the way you know it's a polyatomic ion from its name is if the ending is not IDE. So, if we are dealing with the sulfur ion, this would be sulfide ion. IDE ending. But if the ending is not IDE, you know you're dealing with a polyatomic ion. The most common ending is the 8 ending. And so, the pattern here on the periodic table is based off of the 8 ending. These 2 rows of numbers, these are what you should know. 33443 and 32321. 33443 and 32321. So the top row, 33443, tells us how many oxygens are stuck to the first atom here. So sulfate is sulfur. It's a oxyanion. Oxy means it has oxygen. Anion means it's going to have a negative charge. And 8 by far is the most common. So we find sulfur here, and we come down, and it has 4 O's on it, SO4. Then that thing has a charge on it, and that charge is underneath 2 minus. Carbonate. Carbonate starts out with carbon, so we start with C. ATE ending, it means it's an oxyanion, so there's oxygens here. Find carbon, come down, 3, 2 minus. Underneath carbon there. Nitrate should be an NO4 with a 3 minus charge. However, nitrogen is the only exception to 33443, 32321, and it's highlighted in green to emphasize that, and it's up here in the exceptions box. It's the second one in there. It's NO3 with a 1 minus charge. There are other exceptions up there as well, and they frequently have transition metals in them, or elements that are not here in the P block of the periodic table with the 33443 rule. Those 6 columns there. Hydroxide is a great example. You could say hydroxide kind of sounds like hydrogen and oxygen, but oxygen stuck to other oxygens doesn't make sense. And hydrogen over here, there's no 33443 rule to guide us. So when you're stuck like that, you say check the exceptions, and sure enough, hydroxide is up there in the exceptions, and we find that is OH, IO, with a 1 minus charge. And the one other very common polyatomic ion that is an exception is ammonium. Ammonium is NH4 with a 1 plus charge. And it is the only positive polyatomic ion that we use on a regular basis. Now, I wish it was as simple as there are 8s and a few exceptions. 8s are by far the most common, which is why the 33443 pattern is based off of the 8 ion. However, there are some other suffixes and prefixes that get used with these. And for those, you have to come up and use this box up here. And that box tells you what the suffix is, what the prefix is if it's there, and what change happens to the formula. So, we have persulfate here. I'm going to start with the sulf part of that. Sulf is still S. The ATE ending, heck, the P prefix even, tells me that it's an oxyanion bonded to oxygens. Sulfate, as we did a moment ago, is SO4 and has a 2 minus charge. However, if we come up here to this box, we find that the per8 has 1 more oxygen. So instead of 4 oxygens, we need to change that to 5 oxygens there. ITE ending, again, we base it off of sulf 8, so it's SO, and the ITE ending says take away 1 oxygen. So instead of 4 oxygens as we had originally, it's now 3 oxygens with a 2 minus charge. Hyposulfite, hypoite means we take away 2 O's, and that is from the original sulf 8 ion. Still a 2 minus charge. Those are the most common prefixes and suffixes that are used. And not every element has those exceptions. That is, over here, not all of those end up with all of these combinations. An example, carbonate we did on our examples. Carbonate, there is no carbonite, it turns out. You just have carbonate. There's no variations on it. But you could figure out, theoretically, what those variations should be, or could be, for their formula with just those patterns there. There are a couple other patterns that are listed in this box over here. Again, using sulfate as our base. Sulf means S, 8 means there's oxygens. Over here we find that the bi or hydrogen prefix, means that we add an H in front and we add +1 to the charge. So what was 2 minus, we now add 1 +1 to, and it becomes 1 minus. There is another one that I can't do here as an example because it doesn't actually exist, but the tri-sulfate or dihydrogen sulfate, we would add 2 H's before, and we'd add 2 plus to the charge, and that one would actually end up being 0 if so, which means it's no longer an ion, it's now a compound. The last prefix that can be used is theo, and because sulfur and oxygen are in the same column, they kind of act like each other. And sometimes sulfur will get in there into an oxyanion and take the place of one of the oxygens. So here we replace an oxygen with an S. And then it happens to be on sulfate here because we have S's now. We combine those, S2O3, with a 2- charge. The right-hand box exceptions come up very little. The left-hand box exceptions don't come up much at all either, though they do come up more frequently. Eighths are most common, iths are next most common, and we go from there. By the way, the rules here can apply to the exceptions as well. Nitrate is a great example of that. Nitrate, you start out with the NO3 as your base, and then as it becomes nitrite, you follow these rules, modifying the exception formula. We, of course, can do the reverse process where we name these things. So the biggest thing when naming these is figuring out which prefix-suffix combination to use. So start out, P there is phos, f, and then we have to figure out what ending it is. So we find phosphorus here, and how many O's does it normally have? Normally has 4, there's 4 there, so that must be the ATE ending. And by the way, it does not say 8 here just because I couldn't fit it into the margin, but if you look up here in the box, it does say that the 8 ending C chart 33443. Our next one here, chlorine at the beginning, so that's chlor. And then we need to figure out what the ending is. So chlorine is there, normally has 3 oxygens. This one has 1 less. So 1 less oxygen, we must be looking at the ite suffix, I-T-E, 1 less oxygen, I-T-E. Here we have bromine as our base. So brom, 4. Bromine right underneath chlorine, so it should also have 3. It has 4 here, which means we have 1 more. 1 more must be the per 8. MnO4 with a 1- charge. Mn is there. No 33443 must be an exception. And if you look there, it is. This is per manganate. And all of these are ions. So once we have the polyatomic ions, we can start putting those things into formulas. So here, for example, calcium carbonate. Calcium is Ca. Carbonate, well, ATE means it's not just carbon, it's a oxyanion, so it's going to be CO. And we did carbonate as an example, but just to show you again how it's done, we find carbon, we come down here, there's 3 of them, and it has a 2- charge. Calcium has a 2+ charge, which we can find from here. So then crisscross Ca2, and people get confused on this, and this is why I put the parentheses around my polyatomic ions. You leave the polyatomic ion inside alone. You never change it. You write its formula, and once you've written its formula, you stinking leave it alone. You never modify the formula. I don't know how else to emphasize that. Don't modify the stinking formula. But a number goes outside the parentheses there, and we need to go back to using a pen. 2. Then from here, we can reduce these 2 on the outside to CaCO3. If that really confuses you, I don't know, pretend this is X, and then you have Ca2, X2, and you reduce it down to CaX, and then at the end you substitute XCO3 back in for X. I don't know. To me, that's super easy. Just don't change the formula of the polyatomic ion. The next one we have here, strontium. Strontium is Sr. It's got a 2+ charge to it. Silicate. Well, that's going to be silicon. There's silicon. Silicon should be SO3 with a 2- charge then. So then we crisscross, and we end up with SR2 parentheses SO3 parentheses 2. And it reduces down to SR-SO3. By the way, technically speaking, parentheses are only required when you have a number outside, because you need a subscript applying to the whole thing. Technically, they're not required. I never recommend not writing them. Always put them in there. You will save yourself a ton of headache. Ammonium sulfate. Well, I happen to remember already that ammonium is one of the exceptions on the polyatomic ion chart. It's that one there. You could scour the periodic table and not find it, which is the other hint that it is an exception. Ammonium is NH4 with a 1+ charge. Sulfite, that's going to be sulfur, S. Ite, that's going to be O. 4 is for the 8. Ite is 1 less, so this is 3. And then this thing has a charge, which is 2-. So then we crisscross, and we end up with parentheses NH4, parentheses 2, SO3. Again here, the parentheses required on ammonium because of the 2 subscript on the outside applies to the whole thing. Not required on sulfate because there's no subscript there, but again, highly, highly, highly recommended. And we can even have a compound that is all polyatomic ions. Ammonium, NH4 with a 1+ charge. Hydroxide, OH with a 1- charge. Crisscross the invisible ones there, and you end up with NH4, OH. Of course, once again, we can do the reverse process. Na is sodium. SO4, that's sulf, and sulfur normally has a 4 on it, so ATE. The next one here, K is potassium. ClO4Cl normally has 3 on it, so it's got 1 more than it normally has, so that's perchlorate. And the last one here, NH4 is one of the exceptions. It's ammonium. And OH is another exception. It's hydroxide. There's yet even more with the stock naming system. So we haven't done any of the transition metals yet, and that's because of this box right here. If we wanted to find out the formula for iron oxide, I mean, we could start this. Iron is Fe, oxygen is O. Oxygen's charge is 2-. Iron's charge, there's nothing up above, but next to it here there's 2, 3. Which of those is it? Well, with the transition metals, as well as some of the other metals, mostly things that are in gray boxes on my periodic table here, those require a Roman numeral for the positive charge. The Roman numeral tells you the charge of the metal ion. So, for iron, there's iron 2 and iron 3 oxide. So, we'll start out the same way. Iron on both of these. Oxide is O. And oxide's charge is 2-. That's just oxygen. Now, the new part is these Roman numerals. The Roman numerals are only there for the transition metals, but the Roman numerals tell you the charge of the metal. They do not tell you subscripts. They tell you superscripts, charges, up high. And so then, from there, it's what we've been doing all along, crisscross. So this becomes Fe2O2, which can simplify down to FeO. So iron 2 oxide is FeO versus iron 3 oxide. Crisscross these here, and we end up with Fe2O3. Iron 3 oxide is Fe2O3. 2 different formulas for iron oxide, 2 different iron oxides. All of the ones in gray require a Roman numeral. Now, on my periodic table, I've went through, and wherever possible, I have listed the normal or most common charges that these things have in superscripts there. That does not tell you which one it is. You have to be told that in the name, or you can figure it out from the formula, as you'll see here in just a moment. There are some you'll notice that only have 1. That is simply the most common one. It does not mean there is only 1. If it's in a gray box, it has more than 1 charge. Down here with the lanthanides, I cheated and I put a 3+ beforehand rather than taking the time to type 3 in all of those. And really, these man-made ones here probably should be in gray boxes as well, but I haven't taken the time to do that. Sorry. There are a few exceptions. Aluminum, gallium, zinc, cadmium, and silver all have just one charge. And so they don't go through this multiple charge thing that the others do. And they do not require Roman numerals. I will not penalize them if you put them there, but many textbooks and on the AP test, they won't include these Roman numerals with these substances frequently. They just expect you to know that they have only one charge. Zinc and cadmium are both a 2+. Aluminum, gallium follow their column. It's a 3+, so that's easy to remember. And silver is the oddball one out there with a 1+ charge. But the Roman numerals tell us the charge of the metal ion. So here we have another example, lead, Pb. The Roman numeral 2 afterwards tells us it's a 2+ charge. Sulfide is S, and it has a 2- charge. From there we crisscross, and we get Pb2, S2, which reduces down to PbS. And yes, that is a real chemical with that real formula. In fact, it's one of my favorite minerals, galena. If you remind me in class, I'll pass around a sample of it to show you why it's favorite. Anyway, silver, Ag, and as I said, silver is one of the few that does not require a Roman numeral. You will see on occasion someone will write it as silver 1, but silver is always a 1+, so it doesn't require the Roman numeral. Iodide is iodine, and iodine has a 1- charge, so crisscross on those two, and we end up with just AgI for silver iodide. We, of course, can do the reverse process where we have to come up with Roman numerals. The biggest problem here is people forget that they need a Roman numeral. So here we have chromium, and chromium is a transition metal, so we're going to need a Roman numeral to figure out which of those charges it has. The oxygen part is easy. It's just oxide. The way we figure out the Roman numerals, the way I recommend figuring out the Roman numerals is what I call reverse crisscross. Do the reverse on the crisscross, and you have its charge. So oxygen 2-, yes, that's correct. So then chromium must be a 3+, chromium 3 oxide. We could do the same thing here on this one. So Cu is copper. Copper can be a 1+ or a 2+, so we know we're going to need a parentheses there. Cl is just chloride. And then we can use reverse crisscross. Cu has a 2+, Cl has a 1-, and that's correct for chloride, so then copper must be a 2 Roman numeral there. On this other one here, we have copper again. And we have oxygen, which is oxide, and we're going to need a Roman numeral. If we do reverse crisscross here, there's a bit of a problem. We end up with oxygen at a minus and copper at a plus. 1, if you will, on both of those. And the problem is oxygen's actual charge is not 1-, but 2-. This is a formula that was reduced after the crisscross rule. Well, this is a simple fix. What we do is if oxygen's supposed to be a 2 and it's only a 1 here, multiply it by 2, and we do the same thing to this side, 2. And again, we have copper 2 on this particular example. But that's the tricky part, is making sure that it's not a formula that didn't reduce. And the way you do that is you figure out the charge of the nonmetal. Is the charge of the nonmetal correct? Okay, then you know the charge of the metal. The other way to go about doing that, CuO, copper oxide, you know that oxygen is a 2-. Well, if oxygen is a 2-, what's copper got to be to cancel out? It's got to be a 2+. Great, there you go. Either method works, reverse crisscross or just fiddling around with the charges. You should be able to figure it out. So the hardest thing is adding all these things together. Stock naming with transition metals with polyatomic ions. So I have here an example of that. Iron 3 phosphate. Well, iron, Fe, Roman numeral 3, 3+ charge. Phosphate, that's a polyatomic ion, so this is going to be an oxyanion. Phosphorus is here. It normally has ATE ending, so it has 4 oxygens, and it has a 3- charge. From there, we crisscross. Fe3 parentheses PO4 3, which simplifies down to Fe parentheses PO4 parentheses. The one other hard thing that comes in are hydrated compounds. Hydrated compounds are crystals that have water molecules stuck inside them, and the waters aren't bonded in the strictest sense to the molecule, but they're there and present. They add to the mass, and they affect the chemistry a little bit. And so sometimes when they're there, they have to be included in the name. So this is an example of that. Magnesium, Mg. Sulf is sulfur. 8 means 4 O's and a 2 minus charge. Magnesium has a 2 plus charge. So the main compound here is going to be MgSO4, and I hope you don't mind that I skipped the crisscross and reduce and just went straight to the reduced formula there. The odd part here is this hydrate out here. When we have a hydrate, hydrates use the prefix naming system, Greek prefixes that are listed there, and hepta means 7, and hydrate means that there's waters there, H2O. This crystal has 7 water molecules hidden inside of it. The way we show that is with a dot. That dot does not mean multiply. It is just a dot there. It's how we note that the waters are present, but not bonded to, again, in the strictest sense. Not all compounds are hydrates, and so you don't have to list the hydrates there, but there are some compounds that are hydrated, and when you get rid of that water, you would actually write out that the water is gone, and for that one, it is anhydrous. Most compounds are anhydrous, and we don't take the time to list it because they can't normally be hydrated. But for compounds that can be hydrated, then we would list them as anhydrous. You will never be asked to figure out whether a compound is hydrated or not. You will be told whether it's hydrated or not, and then from there you should know how to name it or how to read its formula. Which brings us to our last set of examples here on the stock naming system, which is the reverse process. So the reverse process here, lead. And lead is in gray, so we got to figure out its charge. S is sulf. There's a 4 subscript there, so 4 is a normal, so this is the 8 ending. And now we have to figure out the charge. Sulfate is normally a 2 minus charge, so then lead here must be a 2 plus Roman numeral 2 in there. Here's another one. CO is cobalt. Cobalt is going to need a Roman numeral because it is here. Cl is chloride. And so reverse crisscross, 3 plus, 1 minus. 1 minus is correct for chloride, so 3 plus is correct for cobalt. And by the way, I know that 1 minus is correct for chloride because of that. So cobalt 3 chloride, and then we have this water of hydration thing to consider. 6 is hexa. I can't read the numbers there, but I have them memorized. You can read them on your periodic tables, hopefully. Hexa, and then hydrate. That's as tough as the stock naming system gets. There's a lot of little things to remember, but overall it's not too bad, and by far the most common thing we do are non-polyatomic ion formulas and formulas with 8s in them. The transition metals don't come up all that often, and the ones that do are super common, like iron and copper. They come up quite a bit, and so it's the easy to work with ones. Be sure if you have any questions that you jot them down and bring them with you to class.